This is a reel of 1.75mm diameter 3D printing filament. Obviously. But what if it's not? Brace yourselves, this is going to get quite technical. Let's go down a rabbit hole, an exactly 1.75mm diameter rabbit hole, for very small rabbits. This video is sponsored by PCBWay, more on that later on. Filament. Plastic pooped out of a hole into a long thin cable of shiny circular potential, ready to be loaded onto your funny machine that can turn it into anything you want. We buy tons of the stuff, probably quite literally in some cases, and we buy it for its colour, its finish, its material properties, maybe because of the brand, but we don't ever think of buying it for its size. Because it's 1.75mm, right? They measure it at the factory, right? To within some parameters that they give us that we never really think of because they look quite small. But let's stop plasticking lyrical and consider the potential issues if it wasn't 1.75mm. If your filament was too thin or too wide, so what? What would happen? The answer is not a lot, to a point. Here's two XYZ cubes. One is over-extruded by changing the flow to exactly 5% more than it should be. The other one is under-extruded by the same amount. So this would be the equivalent of 5% more or 5% less surface area on the incoming filament. Now, I'm saying surface area, that's going to become important. The area of the filament, it's called the cross-sectional area. If you cut it, it's pi r squared, as we know. And so it doesn't mean 5% less diameter. This is the thing. Filament is sold with diameter and tolerances on diameter. But anyway, that is how an incorrect diameter would manifest on a properly calibrated printer, if such a thing exists. But let's entertain the idea that you're printing 15 solid layers and there's nowhere for the extra filament to go. And so you're absolutely going to notice this 5% over or under. How confident are we that the filament we're printing with is exactly 1.75mm? I call this the narwhal. I mean, I could have called it absolutely anything, but it seems like a funny name. This abomination is what happens when I'm on a strict deadline and I need to make a device to demonstrate filament variation over length. It looks marginally less dumb in real life. It's pretty simple how this thing works. There's two wheels to guide the filament through, and the top moves up and down as the thickness varies because the bottom is clamped to the desk. Not, as it happens, enough to make the arrow move particularly well, so the arrow is entirely pointless, unless your filament is really far out, but that's not a thing. This is why it also has this flat bit on the front. I can mount one of these fancy engineering dial gauges here, and it moves when you move the filament. The interesting thing is I can mark areas that move a lot with a pen and then measure them with an actual micrometer, and I can confirm that this thing actually does work to an extent in an incredibly naive way. I was able to identify some particularly thick areas on the filament in the axis that we're measuring here. We'll talk about that, the axis. The diameter of filament in fact varies a lot. I'll show you on this spreadsheet the kind of numbers that I'm seeing. These are measured with the micrometer at semi-random spots on the filament. If you're in the market for a micrometer, by the way, there's two types of micrometers. Some have these vernier scales on them, which means they can measure an extra order of magnitude compared to the ones that don't. You could alternatively go for a digital one, but that's boring. This Oxford brand one seems to be British, made by Cromwell Tools. They're quite reasonable. I paid under £20 for it. However, that said, the digital one that I got afterwards is just so much easier to read. Anyway, with these kind of variances in the diameter of the filament, you would think, would you not, that the extrusion, i.e. the flow rate, would be all over the place. So why doesn't this mean what it looks like it means? Well, it's actually pretty simple. Filament isn't round. The assumption that you can measure filament by measuring its diameter on one axis is substantially flawed. Is filament oval? I don't want to spoil the fun just yet, but it's a reasonable assumption, and it's an assumption that the factories make. If filament was oval, then the actual area is what matters, not the diameter on any particular side. You have to measure the longest diameter and the shortest diameter to get the parameters of the oval and work out the area, and if that's the right amount, it doesn't matter that it's slightly oval. It doesn't matter at all. As long as it fits into the hot end, into the nozzle, it's irrelevant, the shape of the filament. So here's some samples where I've done that to the best of my ability, measuring one axis, turning 90 degrees and measuring again. The area is pi times both of those numbers. It's It's pi r squared, but you average the two axes. Let's just digress for a moment and consider how filament is actually made, as in the factory. And I would like to thank Sunlu for some of the information that's helped me with this section. I sent them a list of fairly technical questions, and they were kind enough to answer them. The process of making filament starts with, and this is weird because I don't know why, but all machines seem to be, the ones I've seen in the photos, they seem to be built backwards, with the raw plastic on the very right-hand side. This is the bit you probably already know about because your 3D printer does it. You are heating up the input plastic, which is probably beads in the case of manufacturers, and you're pushing it out of a hole. The thing is, you probably figured out if you watch my videos, because I say this all the time, there is almost no relationship between the size of the hole and the width of the filament that comes out of it. The filament is pulled through water tanks that are really long and thin, and they essentially cool the filament gradually. At the other end of these tanks there is some mechanism to pull the filament, and just before that typically is the measurement system. The speed you pull the filament at, out of all the things, is the factor that determines the width. I don't know how Sunlu measures the filament, that's a closely guarded secret, but they did tell me they measure what I believe is two axes, and from what I've seen of other machines too, that works out to be a measurement across the x-axis and the y-axis, and then essentially they get a readout of the average of the two, which is exactly the parameter that you can use to determine the cross-sectional area. It's what we just talked about a moment ago. This image from Prusa is clearly not a trade secret because it's on their website. From what I can see, this is using basically two lasers to measure the x and y axis, and it's happening diagonally. Even though measuring two axes is the best method manufacturers have, there is a fundamental, at least theoretical problem with measuring two axes, and this is even if we entertain the idea of oval filament theory for a moment. It's been a while since I got the Play-Doh out, and this is all getting a bit serious, so I reckon I need to show you what I mean visually through a quiz and some Play-Doh. Question 1. What is the cross-sectional area of this circle? Easy. Question 2. What's the cross-sectional area of this oval? We just said it's the average of the two sides times pi. It's still not too bad. Question 3. What is the cross-sectional area of this oval? I think you get the idea here. You can't just measure in two arbitrary perpendicular locations and assume you have what we call the major and minor axes of your oval. You just can't do it. So even if you're an oval filamenter, that's the thing now. I'm going to show you though some real world examples of the cross section of some real filaments after the sponsor section, which is for PCBWay. If you want manufacturing tolerances and clearances to be someone else's problem, then you can design your parts to the specifications PCBWay gives on their website and not worry about whether your machine is even calibrated properly. PCBWay offers manufacturing services across a whole range of processes, including 3D printing, not just FDM but also resin, SLS, which is powder melted by a laser, and metal, which is metal powder melted by a laser. If 3D printed metal being melted by a laser into your custom design doesn't excite you, then you can also have your parts made by using more traditional processes like CNC or sheet metal processing. Also, you can read about all these processes and how they work and how to choose one which is right for you and how to provide the right files, all on the PCBWay website. So follow the links in the description to check them out. And thank you PCBWay for sponsoring this episode. So I've painstakingly cut loads of filament, and I assure you it is not easy to cut cleanly tiny bits without smushing it. If I put one of these under the microscope, it looks circular, but if I then put a circle over it, it's not really, is it? It's close to circular, but it's not circular. Here's some tricolour filament. This looks really cool under the microscope. I've looked at this before and it looked cool then too. But it doesn't look circular, does it? And it doesn't look oval either. It's just whatever shape it wants to be. What's the cross-sectional area on a whatever shape this is? By the time you've worked that out, it's about 2 meters down in the print, so good luck. I'll probably show you some more images now because microscopic images of filament is always cool and I spent far too long on this part of the process. I want to briefly talk to you about the manufacturer's stated tolerances. This is Prusament. When you buy it, you get a chart on the side of the box, and you can actually look this up on the website. But I think deriving meaning from this is another matter entirely. The absolute and standard deviation are over the whole reel, but they are maximum values, so the bulk of the reel will be quite likely to be well below this. I measured a ton of different samples from short sections of reels, and I plotted the deviations that I saw. I should point out that these are taken from a relatively small subsection of the reels because I didn't want to waste, well, pretty much every reel of filament that I currently am using, but I would argue that it's still a pretty good indicator given the average Prusa graph. The filament varies hugely within a short area rather than over the entire reel. I would say there's a good indication that the vast majority of manufacturers do understand this, and they operate to a tolerance of around 2% on cross-sectional area. Sunlu confirmed that they operate on a tolerance of 0.02 plus or minus from 1.75 on the average diameter. This is the case for PLA. Other materials such as wood or marble or ABS, they use 0.03. Now, 0.02 works out, I think, to be about 1 and a bit %, and their results generally do indicate that that's the case. So, what does this mean for FDM printing? I think in some ways it means a lot, but in most ways it means not much at all. While it sucks to not really have an obvious way to accurately measure the incoming filament in any meaningful or accurate way as an end user, and that we have these tolerances in manufacturing that aren't negligible, and they could potentially translate to real flow rate differences. But at the same time, in the tests, I've shown that most manufacturers with a very small number of outliers, they mostly appear to be producing filament that's within fairly stringent tolerance parameters that the leading brands may promise. And there's a lot of processes working together to make the object that you're printing, and to be honest, those are equally or more inaccurate. Retraction, oozing, stringing, losing material on corners due to slowing down, the linear advanced stuff, filament slipping or kinks after the extruder, mathematical rounding on extruder steps, backlash. I could list things all day that are going to have more effect than 1 or 2% on the incoming filament. If you think about it, it's actually surprising that we can get the results that we do get, but also it's not surprising that changing the lighting on these results will often show the harsh reality of the process and its inherent inaccuracies. We are, I suppose, seeing the result of the law of diminishing returns. Prints with modern hardware look good enough, and the remaining challenges, including low single-digit filament % accuracy, they're either too costly or they're not important enough to fix. Of course, if you care enough, then you could buy your filament from a reputable manufacturer. I mean, the bulk of manufacturers are making filaments well within the 2% mark on cross-sectional area in the small tests I did. And in my small sample size, there's a couple of manufacturers that seem to be even tighter tolerances. So anyway, that's where we are. I started this episode with a plan to measure filaments and show you which ones were correct and which ones weren't, and I ended up telling you it doesn't really matter, they're all broadly the same. If you're still bothered though, and this might be a recommendation for you depending on whether you are bothered, it might be worth picking up a cheap micrometer gauge to have ready to check whether that troublesome filament that you're having trouble with is in fact a rare outlier. So this was an interesting journey through filament accuracy. I hope you agree and maybe learned something. Comment below as always, and I will see you next time. Thank you for watching.